Let me welcome you to this lecture. We have now discussed or summarized some of the properties of group 13 elements, or we have looked at the overview of group 13 elements, and now we will proceed to discuss the chemistry of the first group 13 element, that is the chemistry of boron. Now when we look at the kind of compounds formed by boron, what we will realize is that the chemistry of boron is quite diverse as compared to the chemistry of any other element in the periodic table. More importantly, what you will observe is that the kind of structures formed uh, in many of these compounds of boron are quite unusual and are not observed in compounds formed by any other element in the periodic table. Moreover, when you look at when we try to understand the bonding in some of these boron compounds, what we will realize is that the valence bond theory, or the most rudimentary approach to understand bonding in different compounds, essentially fails to explain the bonding in many of these boron compounds. So these are some of the most interesting features of boron chemistry, and we will try to look upon some of these aspects of chemistry of boron. Now, we should first ask the question that why the chemistry of boron, or the kind of compounds formed by boron, are quite extensive, as well as the structures that we observe here are unusual. So the answer lies in several aspects of boron. That is, boron is an element which is, although the atomic radius of boron, atomic size is very small here. Secondly, the ionization energy very high. So that is why boron do not form a simple ionic compounds, and instead it forms only covalent bonds with all other elements in the periodic table. And the third important aspect of boron is that its electronegativity is comparable to the electronegativities of carbon and hydrogen. So electronegativity of boron is comparable to En of carbon and hydrogen. So what it means is that boron can form covalent bonds with carbon and hydrogen, and thus a large number of compounds containing boron, carbon and hydrogen are essentially formed. And these are some of the reasons why the chemistry of boron is so diverse. And what we see is that there are mainly, when we look at the kind of compounds formed by boron, we realize that there are 5 different classes, or we can categorize these compounds in 5 different categories or classes of compounds. So let us classify these compounds of boron so that we can discuss the chemistry of all of these classes of compounds separately. So the first category of compound formed by boron is with metals. So we call such compounds as formed by boron with metals as metal borides. So the metal borides can have any formula, say M5B to MB66. So this is in this case, in the first case, M5B, there are more number of metals. So this is a metal rich boride, while in the later case here, MB66, the amount of, or the concentration of boron is more, and this is boron rich metal boride. So this is the first class of metal boron compound that we are going to discuss about, and we'll discuss about these metal borides in more detail during this lecture. The second class of compounds formed by boron is with hydrogen as well as with carbon. So we know compounds of carbon with hydrogen are known as hydrocarbons. So boron also forms similar compounds with hydrogen, and these compounds are synonymous to uh, uh, hydrocarbons. These are called boranes. Boranes, that is compounds of boron with hydrogen, as well as we can also include carbon in these compounds in the boranes. So then we call them as carboranes. And we can also have compounds where there is a metal present in a boron or in a carborane. So then we call them as metalloboron and metallocarbonate. So again, we will discuss about the chemistry of these boranes, carboranes, metallocarbonates in more detail, and we will also try to understand the bonding in these compounds. As here, for these kind of compounds, here we cannot describe the bonding by using the conventional valence bond theory. So then the third class of compounds of boron essentially are boron trihalides. And then we have the fourth class of compounds that we are going to discuss. Compounds of boron are essentially compounds of boron with oxygen. So these are all these borate. Example is borax is a compound of boron with oxygen. So it is a borate essentially. And then we also have borosilicates. And then perborates, where there is a peroxo linkage in boron oxygen compounds, where there are peroxo groups are present, we call them as perborates. So these are again compounds of boron with oxygen, and again we will try to look at the structure of some of these compounds in more detail during this course. So then the last class of compound formed by boron are compounds of boron with carbon, or more or less what we can say is that these are organic compounds. These can be classified as organic compounds of boron, that is compounds of boron, carbon compounds, or boron. Nitrogen compounds can also be included in this particular category. So these are the 5 classes of compounds formed by boron, and we will try to understand, we will discuss the chemistry of all of these different classes of compounds formed by boron in more detail. So we'll start with metal borides in this lecture. So because the size of boron is very small, it can occupy, the boron atoms can occupy interstitial spaces, and this is how it can form alloys, alloy-like compounds actually, not exactly alloy, but these compounds are like alloys because herein the boron atoms occupy the interstitial sites in a metal. So because these boron atoms can also undergo catenation, and then they can form chains or two-dimensional networks, or as well as three-dimensional networks, which are extremely robust in nature or stable in nature, and this is the reason why there can be a large number of metal borides can essentially be formed. So we have around or above 200 binary metal borides have been already made. So what do we mean by binary metal borides? So these are compounds of one metal with boron. So examples of these binary metal borides already we have given, but then we can write more examples of such metal borides. So M5B, say M4B, M3B, and then we also have M5B2. So here uh, the ratio of metal is progressively decreasing and the ratio of boron is progressively increasing. That is what we see over here. Then we have M7B3. Similarly, then we also have M3B2, and then we have MB, then we have, say, M5B3 is going to come before MB. This is M2B, M5B3, then M3B2 should have been here. M3B2 should have been here. M3B2, and then we have M11B8, then we have MB, and this way one can go on until MB66. There are many more examples, and we have above 200 such binary metal borides with different metals have been already reported, and the structure of many of these compounds have also been found out, and the structure of these compounds are essentially very highly interesting and unusual in nature. And these kind of structures are not generally observed in any other compounds except for these metal borides. So then, apart from these binary metal borides, one can also have non-stoichiometric borides, as well as we can have ternary metal borides, where we have more than two different metals are present along with boron, as well as we can have even more complex metal borides where multiple or different metals are present within the same metal boride. So the examples of these uh, large number of examples of these metal borides have been already reported. Now we have already said that the structure of many of these metal borides are highly unusual and not observed in case of any other compounds except for these metal borides. But apart from this academic interest, these metal borides also has a lot of importance in industry. The reason is there are two reasons. The reason is we can vary the kind of metals in these metal borides, or the stoichiometry of different metals in the metal borides. So by doing this, what we can do is that we can tune the property of these metal borides as desired for different application. And for example, the metal-rich borides, if we take the metal-rich borides, they have properties like they are highly chemically inert. Let's write inert, involatile, and refractory. So what do we mean by refractory is that they are resistant to heat. So these compounds, metal-rich borides, are generally chemically inert, while the metal themselves are not always chemically inert, but we know already, and they are volatile. These are not going to be volatile compounds like the metals themselves, but at the same time, these are refractory in nature. That is, they are highly resistant to heat. In fact, in some of the cases, the metal borides, what we see is that the melting point of the metal borides are more than the parent metal itself, as well as the electrical conductivity of the metal borides are in general exceeds the electrical conductivity of the pristine metal itself. So then, because of these reasons, these metal-rich borides, say for example, metal borides of zirconium, hafnium, niobium, or tantalum, these metal borides have found application in high temperature equipments, say for example, in as turbine blades or rocket nozzles. These many of these metal borides are used to manufacture these turbine blades or rocket nozzles, as well as combustion chamber lining, where because in combustion chamber generally the temperatures are going to be very high, and the linings that the internal lining of these combustion chambers must be resistant to heat, as well as they should be chemically inert, because using a combustion chamber we generally ignite or do reactions, uh, ignite other chemical compounds, and that is why the inner lining must be chemically inert, as well as they must be heat resistant in nature. So that is why the metal rich borides can be used for making all these combustion chamber lining as well. So apart from these applications, another important application that is there for metal rich borides is that we know that boron has got two isotopes, that is 10B and 11B. Now this 10B, the natural abundance is around 20%, while for 11B the natural abundance is around 80%. The natural abundance of course vary depending upon from where you are from where you are isolating the boron. So the origin in different places on Earth, the natural abundance of these isotopes are different, and that is why it is around 19 to 20%, while this is 79 to 80%. Now, when we look at the uh, absorption cross-section of these two isotopes, what we find out that this particular isotope, that is the 10B isotope of boron, has considerably higher absorption cross-section as compared to the 11B isotope of boron. And that is the reason why now these metal borides can be used in nuclear industry as control roads here, as well as nuclear shields, because these metal borides can now absorb neutrons that are present in the nuclear reactors, or to neutrons which are used to carry out the nuclear fission reaction. So they can, when you insert the control rod of this metal boride inside the reactor, what it is going to do is that it is going to absorb the neutrons and thus control the nuclear fission process. At the same time, these metal borides, because they can withstand high temperature, as well as these metal borides can absorb the neutrons, so that is why, or other radioactive particles as well, so that is why they are also used as nuclear shields in such nuclear technologies. So what we have seen is that apart from, of course, metal borides, metal carbides, uh, boro, uh, boron carbides are also used in nuclear technology as control rods or as nuclear shields, because they also are highly volatile, chemically inert, as well as they also have the refractory nature. So both metal borides as well as boron carbides are used, have the same similar qualities. Apart from these boron carbides are abrasive in nature. Also, it is shock resistant. So because of these two qualities of these boron carbides, because they are abrasive, they are used in brake or clutch linings in vehicles, as well as because they are shock resistant, they are used to make these bulletproof jackets or protective armors in aircrafts. So because these boron carbides are light material, because the molecular atomic weight of boron and carbon, we know they are, both of these are lighter elements. So because of that, uh, these are useful for making, and as well as because they are shock resistant, that is why they are useful for making bulletproof jackets or protective armors, because they can withstand uh, the shock that one can get from arms. So what we have seen is that these metal borides, the chemistry of metal boride is quite extensive, as well as they have many applications because of their properties, and we have also learned that they have different, highly unusual structures. So we will now look at uh, the kind of catenation that boron undergoes in different metal borides, or when we increase the concentration of boron in metal borides, what kind of catenations can happen in these metal borides, or what kind of bonding may happen within these uh, boron atoms of these metal borides, or the kind of networks formed by the boron atoms in these metal borides. So when you have metal rich borides, say M3b, so the number of the concentration of boron in these metal rich metal borides are essentially very less, and that is why the boron atoms are isolated or remain isolated within the interstitial space of the metal. So they are isolated boron atoms are present when you have uh, metal rich borides. So as we increase the concentration of boron in the metal boride, so catenation is going to happen, and in case of M3b, what is going to happen is that the dimers, boron atoms appear as dimers within the interstitial space of the metal. So this is how the dimers are going to be present within the interstitial space of the metal in when we as we go on increasing the concentration of metal in metal rich borides. So then once we have MB, what happens is that the chain is present. The boron atoms are all connected in the form of a zigzag chain in metal MB, and then in case of M11B8, the chains are all branched. This sort of branched chains of boron atoms appear, and then in M3B4 we have the chains, essentially the branch chains closes, and what we have an array of hexagons formed by boron atoms are present in case of M3B4, while in case of MB2 we have two-dimensional network of boron atoms are formed in this way. So the extension further extension of this hexagonal chain array happens, and this is how and two-dimensional hexagonal honeycomb like structure of catenated boron atoms essentially are present in case of Mb2. So as you increase the concentration of boron more in boron rich metal borides, these two-dimensional structures are going to now get converted into three-dimensional organizations or three-dimensional frameworks. And what we should note is that these boron-boron linkages are extremely strong in these metal borides, and that essentially uh, uh, these frameworks are extremely robust in nature, and also because of formation of such different types of catenated structures within the metal borides, it also increases uh, the the variability in the composition of metal borides, and that is the reason why we see so many or large number of metal borides are essentially present or can be prepared. So this essentially brings us to the end of this lecture. What we have discussed during this lecture is the reason why the chemistry of boron is so diverse, and why boron forms compounds with unusual structures as well as unusual kind of bonding. So we have looked at some of the reason why this happens, and then we have discussed the kind of or the classes of compounds or the categories of compounds formed by boron. So what we have observed is that there are 5 different categories of compounds formed by boron. So the number 1 is the metal borides. Second one is are compounds of boron with carbon and hydrogen. So that is boron, borane or carborane or metallocarboranes or metalloboranes. Then we have discussed that about another class of compound formed by boron, that is boron trihalides. We know about boron trihalides already. That is BF3, BCl3, BBr3, these kind of compounds. Then the another class of compound are compounds of boron with oxygen, because boron is oxophilic in nature. It loves oxygen, and then it forms compounds with oxygen often. And there are compounds like borates or polyborates or borosilicates as well as perborates. Then the last class of compounds formed by boron are organic compounds, where there are linkage between boron and carbon as well as boron and nitrogen. So we will discuss about all of these classes of compounds formed by boron, and during this lecture what we also discussed about the chemistry of metal borides in more detail. We understood why uh, metal borides are essentially formed because of the smaller size of boron, so that it can occupy the interstitial space of metals, and this is how alloy like these metal borides are essentially formed. And we also discussed the different types of metal borides that are present, either binary or ternary or more complex metal borides, and we have looked at some of the examples of binary metal borides, and then we discussed about uh, the the desirable properties or the kind of properties shown by metal rich borides, which essentially make them highly desirable for different high temperature applications, as well as in case of in nuclear industry also they are being used. And we also discussed about the application of boron carbides in as abrasive as well as a shock resistant material. Then we went on to discuss more about the structure of these metal borides, or the kind of catenation that happens in metal borides, or the kind of linkages or structures formed by the boron atoms in these metal borides. What we have seen is that in case of metal rich borides, the boron atoms essentially remain isolated atoms, while as we increase the concentration of boron atoms in these metal borides, starting from dimer to zigzag chain to branch chain to array of hexagons to two-dimensional networks, as well as more complex three-dimensional frameworks can be formed via catenation of these boron atoms in these metal borides. So this brings us to the end of this lecture, and let me conclude this lecture now. And I thank you very much for being with me during this lecture.